All right, good morning, everyone. All right, so one item of logistics, in case you're not aware, first midterm is Friday, right? Some people have had questions about content. The midterm one is going to span basically the homework up through homework 4. All right, so if you look at the homework, it's gone from a review of 3260 and complex numbers all the way up to moving coil transducers, and that would be the span of eligible exam questions. Oftentimes students ask about what's the general format of the test. Is that your question? Go ahead.
You said determinant of 3, like a matrix of 3. Yeah. So you need to know to do that.
Yeah, we'll use framework tool and all that. Right. So see that. We'll probably have to determine the 3 of the next section. Yeah, so nothing like that. We'll go through that today, actually. It'll be fun. So, what was I say? Oh, yeah. The general content of the exams. Most of my exams are usually around 2 questions, and these 2 questions are multi-part questions. So I always get questions leading up to the exam, like exactly how many problems there will be. I haven't written it yet, so I don't know actually. But the day before the test, you'll get an email that gives you the sketch of the test, which tells you basically how many parts of each question, what each part is worth, etc. And also they'll provide what's going to be at the back of the test, which is basically what content you get as kind of a resource. So in general, it's a Laplace transform table. It's going to be some sort of transformation table to go from decibels to regular magnitude and vice versa. I'm trying to think what else would be on that for this test. That's about it. Open book, open notes for the test. You can bring in a whole encyclopedia if you want. So.
Chapter 19 on the review, that's not.
Oh, okay. Well, I just copied the review from last semester verbatim. We lost a day because of soda. Yes.
If like our book and notes are all digital, do we need to bring in like hard copies of it to use?
Oh yeah, that's good. That's a good question. So if you've been taking all your notes digitally, you can use some sort of electronic device that has them all recorded. I just ask you to sit in front of class, just because we don't want you accessing the internet and talking to your friend, his or her dorm, who took the class last semester, got an answer, right? You don't talking to your friend Wolfram. Wolfram? Yeah, Wolfram. Yeah. Mr. Alpha, right? Yeah. Any other questions about the test? Okay, so this is going to be the most exciting lecture of the whole semester. We're going to go through the dynamics of a DC motor. This usually takes me the whole lecture a little bit longer, actually, to go through. All right. So it's actually quite complex. When I gave this lecture 2 years ago, there were a bunch of high school students visiting to see if they want to become engineers, and the undergrads told me that I successfully drove them away from engineering with this lecture. So, all right, let's do this. So we're just going to go through one example of a shunt motor. And so a shunt motor, if you look back, and we'll just quickly remind ourselves of the differences between a shunt motor and a series motor. So going back, this right here. Oops, not what I want. All right, so this is the shunt motor configuration, or also called parallel motor. So those 2 terms are interchangeable. If I say shunt motor or parallel motor, they mean exactly the same thing. Right? So the differentiating factor between this and a series motor is that shunt motor, parallel motor is wired in parallel. Series motor, of course, then is wired in series. So just okay. So here's a series motor. Showing just a different configuration. Okay, so some elements of the problem statement. Here we have a shunt motor. Okay, the shunt motor has torque constant K tau. Okay, so as a reminder, this is a relationship that gives you the basic relationship between the current through the armature and the amount of torque you get out. It's scaled by the flux, of course. Back EMF constant. Ka. And field constant Ks. Okay, this motor is attached to a rotary inertia. So this is, say, a wheel or some other transmission element that the system is driving. Okay, it has inertia J, damping C. All right, so the problem statement says, find the transfer function between input voltage V and output theta. Okay, so when we say find the transfer function between input V and output theta, what we want is we want a mathematical relationship in the frequency domain between the input. So this would be, say for instance, I had a motor sitting on my desk that's attached to some sort of rotational inertia, and this motor and inertia have the parameters that specify the problem. I want to know if I put a voltage of basically any type, right? So say I can somehow structure what this voltage looks like a sine wave or a pulse signal or something like that. I want to know the Laplace transform of the output, which is motor position, right? So if I had some way to sense, say an encoder or some sort of potentiometer to sense position, I want to be able to see if I can, basically that would be my output, and I want to know what that would be. Right? So that's the basic problem statement. So given that this is a shunt motor, that means I have this wiring diagram. So this is just review from the lecture on Friday. So that means I have terminals, which I can put a voltage across, positive and negative. And then from these terminals, I have two circuits in parallel, the armature or rotor circuit. Then I have the field circuit, or what's in the stator. This is RF, LF, RA, LA, and then we have back EMF constant. I'm actually going to draw this on the other side. So our back EMF, EB. Okay, so this thing is going to be spinning, right? We are looking at dynamics for this problem. This motor is going to be spinning. And then oftentimes if we're saying that we have a mechanical system connected to the electrical system, we'll demonstrate that by just showing a motor shaft then, connected to some sort of rotational inertia. So this is actually C. This symbol, maybe I should draw this a little larger so you can see it a little better. This is not very clear. Okay, so in case you didn't see this in previous books, this is how I usually denote a rotational damping. So this is, usually when we see these sideways lines here, this means that this is the earth or something really rigid. And then oftentimes you'll see for damping is you'll see a bunch of X's in between. That just actually, that represents either bearings or also oftentimes oil in between. So you have some sort of viscous damping in between this rolling element and something fixed. Okay, and then this, of course, has some sort of coordinate data. Okay. All right, any questions about the problem statement? Okay. All right, so we'll start with the one that should be the most familiar, and that's looking at the mechanical system. So if we look at the mechanical system, we want to start to describe equations of motion for this mechanical system. So we have rotational inertia, J. All right, motor shaft, damping, like it's in some sort of bearing. And then I have some, if I want to try to look at Newton's laws, I could say that we have torque in this direction given by tau. We can give a coordinate to this, theta. And then we're going to have viscous damping, C theta dot, opposing that motion. All right, and so then using Newton's laws to describe the equations of motion here, we have the sum of torques equals J theta double dot. And then the sum of torques would be equal to tau minus C theta dot equals J theta double dot. So now remember, we haven't gotten to this yet, but we talked about the static or basically steady state motor conditions. We said that the torque for a motor is given by K tau, the flux from the stator in that motor, and then the current running through the armature. Right? These are the equations that we described. Right? This is the same for the static case. All right. So any questions on the mechanical part of this system? Okay, so the electrical circuit. So this is where it gets more complex. The mechanical system should be pretty familiar to you all. So just recreating the electrical circuit here. Voltage across the terminals. Okay, so this is my electrical circuit, and keep in mind, okay, so if we go back to Friday's lecture, we were looking at steady state operation, right? And so we said in steady state operation, we're going to have a few things. We're going to have constant motor speed. We're going to then have constant applied voltage, and then also constant both field current and armature current. So we talk about dynamic equations of motion. These are definitely no longer constant. Right? So in the steady state motor case on Friday, we said that we can ignore the inductors because the voltage drop across the inductor is equal to L di dt. Right? So now di dt is no longer equal to 0. It's continually changing. so we can't ignore it. Okay, so then the way in which we're going to model this, I find, I mean, you can use Kirchhoff's current law, you can use Kirchhoff's voltage law, whatever you find most comfortable. I think it's easiest to describe motors with Kirchhoff's voltage law, personally. So it's up to you. I'm going to teach it with Kirchhoff's voltage law. Obviously, if you do current law, it's going to work all the same, right? They're equivalent laws. So starting with Kirchhoff's voltage law, so I'll oftentimes abbreviate this KVL. Okay, so if we look at the field circuit, and so when I talk about the field circuit, what I mean is I am looking at the circuit that goes basically through here, right? So we have a voltage that increases from, if we want to make life easier on ourselves and say, all right, let's define a ground, we can do so if we want. And we can say, all right, we're looking at the voltage increase from ground to the positive terminal here has to be V, so that's an increase in voltage of V. I'm going to then have a drop in voltage across this resistor, given by Ohm's law, right? And so I'm going to have a drop in voltage of RF, IF, and then I'm going to have a drop in voltage across the inductor of L, DIF, dt. And then this has to equal 0, right? So if you look at Kirchhoff's voltage law, is that the sum of all the voltage increases and decreases around the loop has to equal to 0, right? So here we're stating one voltage increase across the voltage source, and then 2 voltage decreases across the resistor and the inductor, respectively, and these all have to equal 0. Okay. Any questions about that? Okay, so if we're talking about the armature current or armature circuit, I am talking about then this circuit here. All right, so that's the loop I'm talking about when I look at Kirchhoff's voltage law. And so here I just wanted to we'll just take like 2 minutes or so, if all of you could then write down the equations of motion for this leg of the circuit, and then we'll reconvene and talk about the answer. And then so we just have a little bit of independent work here. If you could write down those equations of motion, then we'll go back to it. Sorry? What do you mean? Power or current times voltage, right? Is power, right? Yeah. Yes. Yeah, so if you look at a lot of really complex models that use it, they use the transmissions, right? Even though the systems transmissions, basically, still have forces are very large too. The inertias are large too. If you're driving a car or a tractor trailer or something. All right. So what do we get? What are the equation of motion for the armature circuit?
V minus IA RA.
Okay, so we have, where's my cursor? So V minus R A I A. Then what?
Minus LA DIA DT.
Yeah. Okay, and then I just for your notes, I forgot the subscript F on the previous equation. Okay, then what?
Plus EB.
Plus EB. Okay, so we'll talk about whether or not it's plus or minus in a second. All right. So I probably should have drawn the battery convention here, or the voltage convention here, but we're saying that by spinning the motor, that the high side of this back EMF is on this side here. So if we look at how the voltage changed from going across this back EMF element, we've actually had a decrease in voltage. Because the high side of this is always going to be higher, or not always, but in this case, be with a positive spin of the motor. This is the high side, this is ground, so we have a decrease in voltage across the back EMF element. So the sign of this is actually going to be negative here, because we've had a drop in voltage across it. Any questions? That does trip up a lot of people in terms of that positive or negative. Then putting all these all together, we have, well, a few things all together here. So we have back EMF, right? Which, if we look at what we did for the series circuit, we said that the back EMF is equal to Ka times phi times theta dots. Okay. Just to note, the reason why I am doing kind of mixing notations here, so we have dot notation for anything that's a mechanical system, and then say, for instance, DIA dt, which usually we think is IA dots, right? The reason for that is because there's a dot on I already, and it gets really confusing if you have two dots right in there. So that's why the notation is a little bit mixed. It just causes a nomenclature issue if we have too many dots flying around here. So anyhow, so we have the back EMF constant, or the back EMF is equal to back EMF constant times flux times then theta dots. And then also, from the series circuit that we're looking at, we have that the flux is equal to Ks IF. Okay, so remember that the flux when we talk about flux, we're talking about the stator that's coming from the field circuit, and the amount of flux is proportional to the current running through the field. Okay. Any questions about the equations of motion so far? I don't know. No. Just give him the book. Yeah, maybe stator. Okay. So in terms of equations, if we want to come up with a numbering system for this, we have equation 1, equation 2, equation 3. Okay. So revisiting our discussions on the moving coil transducers that we talked about, I guess probably on Monday, maybe Friday last week, or Friday last week. No, Monday last week. We talked about how these are combined electromechanical systems, right? So that the equations of motion interact. Right? And so you can see this again, in that we have our equation that mostly describes our mechanical system, right? But the torque on this mechanical system is a function of both the flux, which is related to the current running through the field circuit, and it's also related to then the current running through the armature circuit, right? So it's linked in that fashion. This second equation actually isn't really linked, but then if you go down to the third equation, we see that then the back EMF is a function of the motor speed. So the electrical circuit is linked to the mechanical system, right? So we talk about systems integration, that's exactly what we're talking about. Systems actually, with completely different physics, end up interacting with each other, right? And we have to describe that interaction. All right, so combining all these equations together, combining. All right, so this is just rewriting the equations so they're all in one spot. Okay, these are equations of motion. Right. And now we're trying to work towards getting a transfer function for this entire system, which means a frequency domain, but we have some complicating factors in terms of preventing us from that. So what is preventing us from writing a transfer function for these equations? Yes? Yeah, so we have two currents that are multiplied together, right here, right here, right? So this is a nonlinear expression. We have one more nonlinearity. Where is that at? Exactly. Right. So we have two nonlinear terms in these equations. The second one is purely linear. That one's not going to be an issue. But then the first and the third are nonlinear equations, right? So if we want to do Laplace transforms, then we have to do linearization, right? And so, whereas every problem you've seen before, besides that one little side homework problem, was single variant linearization, this is a multivariate linearization problem. So we're going to talk about that and talk about the methods to do that. Okay. So before we get into that, though, I think it's probably good to look at this in steady state, right? So this should give us equations that look essentially very similar to what we saw on Friday. We're looking at steady state, except the other complicating factor here is we now have some sort of reaction torque on our inertia because we have damping in our inertia, right? So we have this C term in our inertia. Okay, so we're going to assume operating points Assume steady operating points. Okay, we're going to assume that we have a steady velocity for a system for a steady voltage V. So if we label the combined equations 1, 2, 3, so from 1 through 3, all right, so if I have steady velocity, that means that the second derivative is going to be equal to 0. And so I'm going to have then C omega m or omega bar minus k tau ks I f bar I a bar is equal to 0. That's for equation 1 at steady state. Equation 2 at steady state, RF IF bar equal V bar. And then equation 3, RA IA bar plus then KA KS IF bar omega bar is equal to V bar. Okay, so this looks a lot like the equation of motion we had from Friday, except now we have this extra damping term in the mechanical system. Yes? So let me. So either one. So we're just labeling that we have the velocity, the operating point of the velocity is equal to omega bar. So we're just coming up with a name for it. Label. Does that make sense? Yes.
So if we're linearizing like the voltage in omega to be steady like that, would it make sense to make like a could we only really use our transfer function to talk about like a steady input instead of a sine? Like could we still like give the motor a sinusoidal input and get an accurate representation of the output, or no?
Okay. Yeah. So let's talk about what accurate means here. So accurate is a really tough thing to define for the transition from a nonlinear system to linear, and that is highly dependent on the nature of the linear or nature of the nonlinear expression. That's an entire like 7,000 level course in itself that they have out of electrical engineering. So accurate, just keep in mind that accurate, the system has become less accurate as we deviate farther away from the operating point, right, in general. Now, some nonlinearities are really sharp. So if you think of like a 1 over x nonlinearity, right, as you get to x is equal to 0, your linearization gets to be really poor. Right? So it really depends on the nature of the nonlinearity. But I think your question is, okay, so we've linearized with respect to constant velocity, right? Is that going to make, say, positioning type task impossible or difficult, right? Is that kind of your, okay. So in this case, the linearization is not, well, there is no term that just looks like, it's just theta, right? There is not a single theta term in here, right? So we have theta dot, which is coming from the speed of the motor. Okay, so in that sense, without getting into too many details, we are safe to do so because there's not a nonlinearity in theta. If there was a nonlinearity in theta, like what you see with, actually with your problem that you have for the project, right? You have a sine theta term, then we would not be doing this about some sort of steady motor velocity. If you look at also what we did, the homework problem, or the project, we were doing this with a steady position, right? Does that make sense? Okay. So we have these static relationships here. We can also write down our whole chain of operating points too. So we can write down that we want we have an operating point for the velocity we said is equal to omega bar plus omega hat bar, right? So this is just like in the project, you had to write all these expressions in terms of doing a change in coordinates. If we look at the next derivative of this, taking the derivative, we get theta double dot is equal to omega hat dot plus, sorry, omega bar dot, omega hat double dot. This is steady, right? So this is going to go to 0. With all our currents, we can do the same. And if I take the first derivative of the current through the armature, this is looking at the first derivative of I bar, and we said we had steady current, or steady voltage, so therefore steady current. This goes to 0. Same thing with IF. This all goes to 0. And then last one to concern ourselves with is voltage. All right, and so these are going to be all of our transformations for this multivariate linearization. Yes?
We assume the currents to be constant.
Constant, yeah. Okay. Okay, so for those of you in homework, I think it's 1, homework 1 who chose to do the multivariate linearization problem, you have seen that multivariate linearization is just multivariate Taylor series taken out to first order, right? And so then the expression for this is if we have some sort of function in 2 variables, we can write this function as the function evaluated at the operating point for those 2 variables, plus then, instead of regular derivatives, we're now talking about partial derivatives of this function evaluated at the operating points, x minus x bar. Okay, so just a note on how this proceeds, right? So I'm taking the partial derivative with respect to x. So that means my deviation variable is going to be x minus x bar. the next one, I'm going to take the partial derivative with respect to f. Or with respect to y, I mean. Okay, so this is going to be our template for taking linearization for all the next terms. Okay, so if I look at equation 1, all right, so we said equation 1, which is right here. All right, so equation 1, if we want to, I'll go through the first one carefully with every single variable in there. All the linear terms are going to end up being linear after we do this. Nonlinear terms will, of course, not be nonlinear still. But we'll do this kind of in a very careful manner, and then we'll go through a little more quickly for the next ones. So if I look at f1, so f1, f2, f3, these are all different functions, right? f1, if we look at all the variables in f1, it's a function of theta double dot. It's a function of theta dot. It's a function of if. And it's a function of IA. And so doing the multivariate linearization, I would say then that this is approximately equal to J theta bar double dot plus C theta bar dot minus K tau Ks IF bar IA bar. Right? That's my function. Now I'm going to take the partial with respect to the very first variable here. Right? So this is 2 variables. Here we have 4. So we take the partial with respect to the very first variable. I'm going to get the very first variable is theta double dot. So I only see that in one location. So my first variable is going to be partial of this function with respect to theta double dot. That just gives me j, nothing else. Theta double dot minus theta bar double dot. Okay, so we already said that theta bar double dot is equal to 0, right? All right, next variable. Partial of function 1 with respect to theta dot. So that equals c, right? And that's it. And then we have our deviation, which is theta dot minus theta bar dot, which goes to omega bar, right? All right. Next variable is how do I list this? IF. Right. So we take the partial of this function with respect to IF. That's going to give me negative K tau Ks IA. And then I evaluate this function at our operating points. This gives me IA bar, IF minus IF bar. All right, that's the trickiest one yet. Any questions about that individual term there before I get to the next one? Yes? Yeah, they merged. Okay. Last term, K tau, Ks, partial with respect to IA, right? So that's going to be K tau, Ks, IF, evaluated at the operating point, IF bar, IA minus IA bar, and then it's all equal to 0. Any questions on that? Besides a lot, this is the first time you've seen this. Okay. Yes?
So we're taking the partial derivatives of all of those terms.
Every single one of the terms, yeah. And I'm doing it in the very long form now for the first introductions to it. I think if you do enough of these, you'll start to see a pattern, and you'll see that like the linear terms will just skip right through because it's always going to be linear. So I will mention that maybe I shouldn't say this yet, but midterm 2 will have multivariate linearization on it. 100% guaranteed. Okay, so you should know this. Yeah. Yes. Yes.
So did we do it, did we include C omega? Did we include omega? C
Yeah, it's this term right here.
I'm just confused why it's equal to 0. I guess the other one.
Because yeah, so function 1. If you look at on the left-hand side, function 1 is equal to 0. Okay. Some simplifications to make our lives easy here. So we know that theta bar double dot is equal to 0. What else can we cancel out here? All right, so we have this expression. We know that theta bar dot is equal to omega bar. Right? We also know that C omega bar minus K tau Ks IF bar IA bar on the left-hand side is all equal to 0, right? So here I have C omega bar minus K tau Ks IF bar IA bar, right? So that means this all equals 0, right? So this whole thing can go to 0, making our life easy. So I did this in the long form just to show you how all this cancels out, but the constant terms are always going to cancel out if you do multivariate linearization and look at the steady operating parameters and basically evaluate the system at steady state and plug that back in. The constants will always cancel out. All right? This is just showing why, but with a little practice, you can, if you want to save time, always just have those go to 0 if you want. Okay. Other terms that are going to make our life easier is that we know that theta double dot from down in this bottom left is equal to theta hat double dot. So we're trying to get everything to be in hat variables, just like you did in your project. So that means that this can go to theta hat double dot. This whole term can go to theta or omega, or I guess theta hat dot IF minus IF bar. So if I look at this expression, if I were to move IF bar to the left-hand side, that's going to be IF minus IF bar. That equals IF hat. Same thing with IA minus IA bar goes to IA hat as well. So when I simplify this expression, it's not going to be all that complicated after I crossed a lot of things out. So this is going to be equal to J omega hat double dots plus C omega hat dot minus K tau Ks IA bar IF hat K tau Ks IF bar IA hat all equal to 0. Yes?
Sorry, what is the third of the C term? I thought it was theta hat dot minus omega bar. Is that second or third?
Yeah, that's correct. So that's coming from this offset that we defined here, this translation in variables here. So if we were to, what we had here was, sorry, we have a lot of lines going everywhere here, but we have, before this we had theta dot minus omega bar, right? So if I were to move on the left-hand side here where I circled, if I were to move omega bar to the left-hand side, I'd have the same thing, and that equals theta at dot. Okay.
The KTKSIFIA.
Yeah.
What are they gonna do?
Up here, right? You're talking about in this region? Yeah, so that's coming from evaluating our system at steady state. This canceled with the C omega bar minus K tau Ks IF bar IA bar. Okay, so we have about 5 minutes left. So I'm just going to write down what the third expression is going to be, or sorry, the second expression is going to be. I think in the last 5 minutes, it may make sense for you to try and basically take the methods that we looked at or used for equation 1 and try to apply them in equation 3. So we'll take about 4 minutes, and then the last minute we'll reconvene and see what we had, and then we can revisit this again on Wednesday to check our understanding and everything. So if you could just take the last 4 minutes or so, well, then we'll talk about that. So it'll be equation 3. Because I put a hat in between, so it separates it. see it now. All right. So does anyone have an expression they think is right, or do we want to wait till Wednesday? You got it, Carson? All right. So what do you got?
I've got v hat equals
What is this? What do you have? Yeah, third equation. Yeah.
v hat
Okay. V hat equals. So we'll put this all the way over here. Okay.
I a hat r a
Okay.
plus l a I a hat dot
Okay. So
plus l a
okay.
plus k a k s I f hat times theta r dot
Okay. So IF. Okay. So IF hat or which one?
I f hat
IF hat times what?
times theta bar dot
Okay. So do omega bar, right? Right.
plus k a k s I f bar theta hat dot.
Okay. So that's correct. We're out of time, so we'll go back through this carefully on Wednesday, and we'll run through why this is the case. But it's if you want to, if you're still interested in this, you didn't get it the first time, you can go back through, it's in between now and Wednesday, and try and get this expression. All right, more fun on Wednesday.